Hello, thank you for coming to my talk. My name is Jaikumar Radhakrishnan. I work at the Tata Institute of Fundamental Research in Mumbai. The topic of my talk is two-coloring non-uniform hypergraphs. This is joint work with Aravind Srinivasan of the University of Maryland at College Park. Hypergraphs. A hypergraph is a collection of subsets of a vertex set. The elements of the collection are referred to as edges or hyperedges. The hypergraph F is R uniform if every edge of F has exactly R vertices. By a uniform hypergraph, we mean a hypergraph all of whose edges have the same number of vertices. Two coloring of a hypergraph is an assignment of colors red and blue to the vertices such that every edge receives both colors. It is a hard computational problem to two-color hypergraphs. It is known that it is NP hard to determine if a given three-uniform hypergraph is two-colorable or not. It's also hard to approximate in the following sense, that given a two-colorable four-uniform hypergraph, coloring it with log n to the epsilon colors is NP hard. So if we assume P is not equal to NP, then it is hard to color two colorable four uniform hypergraphs with log n to the epsilon colors for some epsilon. So the focus of this talk is not the computational or complexity theoretic results surrounding two coloring of hypergraphs. We'll focus on a certain combinatorial problem associated with two coloring, which arises out of random coloring methods for hypergraphs. So a natural way of two coloring hypergraphs is the following. You assign to each vertex a color red or blue independently, each with probability half. Then the expected number of monochromatic edges is given by this expression. So if all the edges of the hypergraph have at least k vertices, then this expression would be the number of edges in this hypergraph times 2 to the power negative of k minus 1. So if this hypergraph has fewer than 2 to the k minus 1 edges, then this expectation would be less than 1. In particular, the hypergraph would be two-colorable. So a random algorithm, which doesn't even look at the hypergraph and just colors the vertices red or blue, succeeds in coloring hypergraphs which have very few edges. Motivated by this, Erdős defined the function g of k. So we restrict attention to hypergraphs which have at least, whose edges have at least k vertices. And then g of k is the largest L such that every hypergraph with m of f less than L is two colorable. So let me explain. If this expectation is less than 1, then we know that the hypergraph is two colorable. But what if this expectation is 5? Can we start with this random coloring, which would perhaps on average leave fewer than 5 edges monochromatic, and modify the coloring or find another coloring that would color the graph perfectly? So is it true that every graph that is simple enough to leave only a small number of monochromatic edges when colored randomly admits a two coloring, which is constructed perhaps slightly more carefully? So the largest L for which it is possible to two color the hypergraph under the assumption that the expected number of monochromatic edges in a random coloring is at most L is called G of K. And Erdős asked for bounds on G of K. So an early result of Beck showed that G of K is omega log star K. So let me say it again. If a hypergraph, all of whose edges have at least K vertices, if that hypergraph has the property that a random coloring leaves fewer than log star K edges monochromatic, then that hypergraph admits a two coloring. This result was improved to log K recently. Better bounds are known if we impose some restrictions on the hypergraph. For example, if we insist that the hypergraph be simple, that is, every two edges that intersect must intersect exactly on one vertex, then we can get a polynomial lower bound on G of K. A different result, somewhat older, says that if we insist that all edges have size exactly K, the definition of G of K allows edges to have size at least K. But if we insist that all edges have size exactly K, then for such hypergraphs, G of K is at least square root K over log K. So better bounds can be obtained if we put some restrictions on hypergraphs. So the focus of this work is if these restrictions can be relaxed somewhat. So this motivates our definition. So we have a hypergraph F, and we will call it lambda approximately uniform if the ratio of the sizes of any two intersecting edges is at most lambda. So consider any two edges that intersect on one vertex, then the ratio of the sizes of those two edges must be bounded by lambda. So think of lambda as a large number, 10, 20, perhaps square root log K. We don't insist that the intersection sizes all be 0 or 1. Edges are free to intersect in more than one vertex. But whenever two edges intersect on one vertex, the ratio of their sizes must be bounded by lambda. Under this assumption that your hypergraph is lambda approximately uniform, it doesn't have to be uniform, it is approximately uniform, then we get better bounds on this quantity G of K. That is, graphs which have even larger number of edges can be two-colored. So I would like to use the remaining time to explain how this result is obtained. But before that, let me give you some examples of parameters that arise out of this expression. So this is a slightly awkward expression. Let's look at it. So it involves a maximization over a parameter alpha, and then it is a minimum of these two quantities. Okay, so for example, I have just reproduced the expression here. If you set lambda equals 10, then you can choose alpha appropriately and get this sort of a result. That is, those hypergraphs where intersecting edges have ratios at most bounded by 10, then the G for that such hypergraphs grows polynomially in K. On the other hand, if we allow for a greater disparity in the sizes of the intersecting edges, then we get a bound of the following form, which grows faster than log K, which is what is promised by previous results, but doesn't quite grow polynomially. In general, whenever lambda is little of logarithm of K, we get improvements over the previous results. Okay. So let us just look at how these results are proved. The basis of this result is a random greedy algorithm of Cherkashin and Kozik, which they used for coloring uniform hypergraphs. We observe that a certain modification of the analysis of that algorithm, the algorithm stays the same, yields the new results. So what's our input? The input for the original algorithm of Cherkashin and Kozik was a K uniform hypergraph. Later on, we will use it for hypergraphs which are only lambda approximately uniform. Okay. But the algorithm goes as follows. First, you order the vertices of the hypergraph randomly. So if it has n vertices, there are n factorial possibilities. You pick one of those possibilities at random, and then you start working one by one on the vertices in that order. Each time you color the vertex red, unless coloring it red would make some edge monochromatic. That is, suppose there was some edge and you had colored the previous vertices red, and this vertex that you're currently considering is the last vertex of that edge, and you're about to color it, then you should not color it red, because that would make that edge monochromatic red. So you color it blue. So this is the algorithm. The only randomness is in this step. You choose the ordering at random. After that, it's a deterministic algorithm. So how was this result analyzed? So what Cherkashin and Kozik showed is that if your graph has fewer than these many edges, now it's a K uniform hypergraph. So if your hypergraph has fewer than these many edges, then this algorithm will produce a two coloring with positive probability, okay? Which says that if for uniform hypergraphs, the G of K is at least square root K over log K. Now, let us see how the analysis proceeds. And we are still working with K uniform hypergraphs. I'll tell you later how we adapt their analysis. So the first observation is that we never make any edge completely red, because when the last vertex of that edge was being considered, we would have made it blue, made that vertex blue. Okay. So the only possibility, the only way this algorithm can go wrong is that it might produce monochromatic edges which are entirely blue. And let us see how that might happen. So suppose there was an edge and all its vertices were somehow forced to become blue. And why would that happen? Suppose there was an edge and its previous vertices were all colored red, and there was this vertex, which was the last vertex, and we were forced to color it blue. And it could be that later on, when this vertex was being colored, there was a similar situation, and some other edge was almost red, and we were forced to make all these vertices blue, one after the other, for various reasons, each time to save some other edge from becoming red. But in any case, whenever an edge is made blue, there is a first vertex of it, which was painted blue. And that would have been painted blue because there was another edge which was almost red. And these two edges shared a single vertex. So you can check that whenever an edge is made blue, there is an edge E to blame, which has this configuration. That is, it shares only one vertex with it. And this vertex in the ordering appears between the other vertices of E and F. So we will analyze the probability that some edge ends up blaming some other edge for making it blue. Okay. So that is how the analysis will proceed. So let me give you some more details. So instead of arranging the vertices at random uniformly over by choosing a permutation, let's assume that each vertex is given a random delay in the real interval 0 to 1. So each vertex is assigned a delay, and then we consider the vertices in the order of that delay. Now we will choose a parameter delta. The point is that if there is an edge and all its vertices have come very early in this line, that is, their delays are very low, then such an edge is likely to be blamed, because if you look at its last vertex, there might be an edge on this side which has that vertex in common with it, and maybe it blames this edge E for making it blue. Okay. So whenever an edge has all its vertices in this initial interval, we say that this bad event happens. We give up on this edge. This edge has become very vulnerable. Similarly, so this edge has become very vulnerable to be blamed. Similarly, if there is an edge, all of whose vertices appear in this region, whose delays appear in this region, we again consider that a bad event, because it's likely that all its vertices are somehow the last vertex of some edge, and they are forced to become blue. Okay. So these are vulnerable edges, and whenever some edge F blames some edge E, it is either the case that one of those edges was already vulnerable, that is, it fell into these events, or that neither of them was vulnerable, and nevertheless F blamed E, in which case the common vertex between F and E, recall that whenever F blames E, they have a common vertex. That common vertex must fall in this black region, and the other vertices of E and F should fall on either side of that vertex V. So it turns out that the probability of failure of our algorithm, and whenever the algorithm fails, some edge blames some other edge, can be bounded by the sum of the probabilities of these events, and this quantity can actually be analyzed. Okay, so in the analysis of Cherkashin and Kozing, if the number of edges in the graph was something like this, like L, where F is actually L times 2 to the k minus 1, then one can bound the sum of the probabilities of the three events by this quantity. And one can show that if L is something like square root k over log k, then one can choose delta so that this probability of failure is strictly less than 1, which means there is a coloring. That is, this random greedy coloring, which colors vertices one by one, will, with non-zero probability, successfully color this graph, successfully to color this graph using colors red and blue. Now I want to tell you how we use this algorithm to show our result. Okay. What's the difference? The difference is that in our case, the edges are not all of the same size. We are not looking at uniform hypergraphs, only approximately uniform. And even our constraint of approximate is rather weak. Only intersecting edges are required to have their sizes somewhat similar. So instead of having a uniform value delta for all edges, we tune the value delta based on the size of the edge. So we will again have these three events. E1 says that E is vulnerable. E2 says F is vulnerable. But when is E vulnerable? If all its vertices receive delays in this region, and in this case, the delta E depends on the size of E. Okay. Similarly for F. So if E is large, then delta E is small, and we allow a bigger space for E to be called vulnerable. So once these events are defined in this fashion, the rest of the calculation is the same. Okay? So the probability that the algorithm fails is bounded by the sum of these three probabilities. And let us look at these three probabilities in somewhat greater detail. The first expression corresponds to the probability that E is vulnerable. And for that, the probability that all its vertices fall in an interval of this length is given by this expression, which is not hard to approximate or bound. Similarly, the expression for F can be bounded like this. And the probability that E ends up blaming F and these two things don't happen, these two events don't happen, corresponds to the common vertex being falling in this range, that is from half minus delta E to half plus delta F. And that probability is this time computed using this integral. Okay. And that goes from minus delta E to plus delta F, corresponding to the left and the right boundaries of that black interval on the previous slide. This expression is bounded. The total probability is bounded by this quantity. And these integrals are not hard to evaluate. And the final expression that comes out of this is this. One needs to do some work, technical work, to obtain this bound. Once we have this bound, we combine it with these two bounds and get the final result, which was the main claim of the paper. So I do not want to tell you about these technicalities. They are not very illuminating. They do not have any combinatorial or algorithmic content. It is just you get some expressions. There are technical difficulties because this F is not equal to E. When F is equal to E, this expression becomes 1, and the integrals are particularly simple. The value they'll give out are particularly simple. But when F and E are not of the same size, the expressions are awkward, and some work is needed to analyze them so that we can get some bounds out of them. Okay. So let me conclude. So we show better bounds for two coloring hypergraphs. In particular, we show better bounds for the function g of k defined by Erdős. So these were two examples which I had shown earlier. So we hope the ideas contributed by this work will eventually help in getting better bounds for the original function g of k. We did not address the original function. We imposed a restriction of lambda approximate uniformity. For the original function, the bounds remain log k on the lower side and order k squared on the upper side. Thank you very much. I look forward to seeing you at the conference.